So if you remember, we were essentially looking at an example related to critical state theory. And so I essentially formulated exactly the same problem, this wedge-shaped hopper with smooth frictionless walls and with gravity acting in the radial direction. And as in this problem, there is no velocity in the theta direction, and there is also no dependence of any quantity in the theta direction. But when we solved it the first time, we said rho bulk, that is the bulk density, is a constant. But in this case, we take it to be a variable. And in our critical state theory, in addition to the balance equations, we have the yield function, the associated flow rule, and the coaxiality condition. So in the last class, we saw that we have this as our continuity equation. That's equation number 1. This is the momentum balance equation in the r direction. This is equation number 2. Then we applied the coaxiality condition and we found that dr theta is equal to 0. So that means d theta theta and drr are the principal coordinates, d1 and principal components, and so that gives us d1 and d2. And then from the coaxiality condition, since stress and strain rate must be collinear, so then the principal stresses are sigma 1 and sigma 2 are sigma theta theta and sigma rr. And of course we can relate the rate of deformation tensor components drr and d theta theta to the velocity vr. Then by applying the flow rule, that is, say, the flow rule, if you remember, is just something like d1 is equal to lambda into del f by del sigma 1, and similarly d2 is equal to lambda into del f by del sigma 2. So this is the flow rule. We divide one by the other, so you have d1 by d2, and then you have ratio of del f1 to del f2. And since we know we can always write sigma 1 and sigma 2 in terms of sigma m and tau max. And so then using the yield condition, we can get this equation, which relates the principal components of the rate of deformation tensor to the yield condition. And in here, alpha is the ratio of sigma m by sigma c. And sigma c is a material function which depends only on density. So this is using flow rule and yield condition together gives us this. And then the yield condition itself is given by this equation, where tau max is sigma c sine beta into this quantity, which depends on alpha. And alpha is just the normalized value of the mean stress sigma m. And of course, tau max and sigma m are related to the principal axes, principal component sigma 1 and sigma 2 in this way. So if you actually look at this, in all of this, there are only 4 unknowns: rho b, Vr, sigma rr, and sigma theta. These are the things we have to find out. And we have 4 equations. So that essentially is the complete formulation of the problem. And we can solve it. I'm not going to do it. I mean, if you want to solve this, you have to solve it numerically. But there is an approximate solution possible, and I'll put a handout which shows how you can do it. If the change in density is very, very small, then you can get an approximate solution, and I will put the solution up on Moodle. Then we very briefly looked at flow in hoppers and so forth. This hopper has essentially either a wedge-shaped or a conical bottom, and then a cylindrical or a rectangular top. And this is what is the desired flow pattern, that you want this type of mass flow where all the material flows out. And this is not desired, where you have stagnant regions and the flow happens only in the central part. To prevent this, we have to make sure that the hopper angle is small enough and that we have low wall friction. So then it prevents this stagnant zone formation. Another thing that's very important in these hoppers is that if your exit opening is not large enough, you can form an arch across the exit, and that completely blocks the flow. And those arches can be quite strong and withstand a huge amount of weight from the top. We also, just before we stopped, we said that if the height is more than about 2.5 times the exit diameter, then the mass flow rate is independent of the height. And in fact, if this diameter is more than about 2.5 times the orifice diameter, then the mass flow rate is independent of the diameter of the hopper as well. And I just mentioned briefly that what this essentially gives us, that the mass flow rate depends only on in terms of the geometry, it only depends on the diameter of the exit. And I'm going to talk today about this correlation which relates mass flow rate to d0 in a little while, and that is called the Bevel-Loop correlation. And then after we finish that, then I will talk about rapid flow. So we were talking about very slow flows completely dominated by friction. Now we'll talk about rapid flows where collisions between particles become important. And then I'll define this granular temperature and then governing equations, and then we'll do some examples. Okay, so any questions? So let me share the thing again. So we were talking about all this last time in the last class. Lecture 21. That was yesterday. So today we are on lecture 22. And the date is 21st of September. So it's 21/9/21. That's a nice date. So, we want to essentially take off from what we said last time, that essentially there is no dependence of any of the geometrical parameters on the mass flow rate out of the hopper. So we can do some amount of dimensional analysis. So if, let's say, we have our hopper like this, and let's say this distance is d0, and if none of the geometrical parameters are important. And if you want to calculate what is the velocity coming out of this, then from dimensional analysis, what we'll see is that the velocity at the exit should be proportional. If it only depends on d0, then the only other way we can make it dimensionless is to multiply it by g times d0 and put it equal. So velocity should be equal to this, correct? Where g has units of length by time squared multiplied by length. So this product has units of length squared by time squared. When you take the square root of it, you'll get units of velocity. So this is the typical velocity that we will expect. And then if you see what is the mass flow rate is just velocity into the area of flow times the bulk density. Now the area is just equal to pi d0 squared by 4. So we can write down that the mass flow rate must be proportional. So I'll not bother about pi by 4 because I'm not writing any constants here. So instead of V0, we'll write G times D0 raised to the power of half. Then A0, I'll just write it as D0 squared times rho B. So this is just equal to rho B into G raised to the power of half and D0 raised to the power of 5 divided by 2. So dimensional analysis tells us that mass flow rate should be proportional to the diameter of the orifice raised to the power of 5 by 2. So if this is the case, then if I make a graph of d0 raised to the power of, so if I do it the other way around, if I plot mass flow rate raised to the power of 2 by 5 versus d0, then I should get a straight line. And Bevelou was one of the first to show this in 1961. But in fact, it was even before that, there was another very famous name, Hagen, in 1895, who also found this, working with hourglasses. Hourglass is basically, that a container full of sand, and then you see the sand falling, and it's often used as a timer. So in those days, when there were no clocks, this was considered a very nice way of keeping time. And he also found that the mass flow rate is independent of height and so forth. So it's a good way of keeping time. So this is the same. You would have all remembered the flow, Poiseuille flow in a pipe. That is the Hagen-Poiseuille equation. That is, he's the same person. But when Bevelou did these experiments and he did systematic experiments, he in fact found that the data does all fall on a straight line. But if you extend the line to zero mass flow rate, what he found is that it doesn't go to zero, but it goes to some finite intercept over here. So that means, what does this mean? That means actually it's not that your orifice diameter has to go to zero for the flow to stop, but it goes to some value, and this intercept is found to be proportional to k times the diameter of the particle. So now if you look at this equation, then you see that it's not proportional to d raised to power of 5 by 2, but it actually turns out to be that if you take this into account, then you see that m raised to the power of, what you actually find out is that m dot raised to the power of 2 by 5 is proportional to d0 minus k into dp. So this is what gave him the correlation. So he finally came out with this correlation, which is some constant, which depends on all these other factors that we have been leaving out. Plus over here also, there will be some prefactor to the velocity which we have left out. So you put all those things into this constant C, and then you have density, bulk density of the material, and then this, and then of course g raised to the power of half, and then you have d0 minus k dp raised to the power of 5 by 2. So this is what is known as the Bevel-Loop correlation. Of course, Hagen also had come up with the same thing many years before, but didn't do it in the same with the same level of detail as Bevel-Loop did. So now this is called the Bevel-Loop correlation. Okay, and so this is an easy way that you can estimate the mass flow rate. Here K is approximately equal to 1.5 for spherical particles, and it's larger if the particles are angular, and then C is about 0.55 to 0.65. Okay. So this is very useful. You can easily find the flow rate out of this hopper using a simple equation. Now with this done, let us now go on to the next thing, and that is, let us now look at
Sir, Kunal here.
yeah.
Yes, sir. So in the above graph of m raised to 2 by 5 versus d0, if the particles the dp is too small, the particle size is too small, then will there be any change in the curve, sir?
No, it doesn't matter. You get that. So you get closer and closer to the origin. That's all.
Yeah, and the straight line will be adjusted accordingly, right?
Yeah. So the straight line will shift, but the key the key reason is that it's all dependent only on the what should I say, the mass flow rate out of the hopper is basically just dependent on what is happening here. So this is the you can say this is really where all the resistance to flow is only at the exit, and so that's why the the other dimensions don't seem to matter very much, because as long as you're continuously supplying particles to this region, then whatever is the maximum that this the flow can sustain through this is what will determine. So, and we know that in all our granular systems that the stress, once you go above a certain height, the stress becomes a constant. So that is one reason you can imagine why the mass flow rate is independent of height, it's independent of the diameter of the bin and so forth. And really, I mean, though I have shown it for hoppers, there are also many cases where instead of instead of a conical section at the end, people just use a straight. So this is usually called a bin, where you have either a cylindrical or a rectangular cross section, and the material is flowing out at the base. And in this, you of course get stagnant zones, but in many cases you may not be bothered about it. So very often in the case of free flowing materials and all, people may use just a simple bin for storage and for supply of material to a process. Okay.
Yes, sir, one more thing, that K times dP part shows, I think, the choking that we have discussed yesterday, right?
Yeah, well, this is like, you've got to remember that in most practical applications, you're talking about the arch formation, right?
Yes, sir, yes, exactly, yes.
This one is much smaller than the. See, the practical situation, maybe the particle size is maybe 100 microns or 200 microns, and the diameter of the orifice may be 10 centimeters. So usually this will have a very small effect in most practical, that is, the K times dP will not have a big effect unless you're dealing with large particles. So, but that choking is something different, because when the particles form an arch, usually there is some level of cohesion between the particles so that you can form such a huge arch. If the particles are very freely flowing and they don't stick with each other, then the arch formation happens only if the orifice diameter is of the order of 6 particle diameters. If you go more than 6 particle diameters, then for smooth particles, you'd never form arches. But in practice, because the particles are slightly sticky and they have some cohesion, so even in very large uh, diameters, you can form an arch.
Yes, sir, thank you.
Okay. So the choking is slightly more complex than just K times dP. This K times dP is only a small correction to the flow rate, but it won't explain choking.
Yes.
Okay, so here we are looking at the case where you actually have the inertial number. So now we are jumping to a new topic, and we are looking at rapid flows where the inertial number I is larger than 0.1. And in this case, you will have momentum transfer by collisions between particles, as compared to slow flows in which momentum transfer is entirely by friction. So here we make an analogy with molecules. So that is, you pretend that the particles are molecules, and so then you can use all the theories that people have developed for molecules and then use them to try and describe granular flow. So you can just say you can adapt kinetic theory of gases to granular flow. Okay. But there are, of course, differences between molecules and particles. The first difference is, of course, that interparticle collisions are inelastic. We have already seen this, and we have calculated also the time for inelastic collapse. So you just imagine these two situations, okay? You take a bottle full of marbles and you shake it up. So then when you shake it, then the particles get some energy. But because that energy is so quickly dissipated by collisions that if you shake these marbles and you put the bottle down, everything will settle and it will be at rest. On the other hand, you look at the same thing, you take the same jar and fill it with water. And if you look at the molecules, those molecules are constantly colliding with each other. But the collisions are elastic. So it just remains in the liquid state and it maintains its energy. It does not, that energy just doesn't dissipate on its own. And that's why it maintains a liquid state. So because of these inelastic collisions, you have to continuously supply energy to granular systems if you want to keep them in a fluid state. The second thing is that particle-particle interactions have friction. And really there's no force like that between two molecules. So this is a very unique kind of force. And then the third thing is, of course, the size. So particles are typically 10 raised to the power of 18 times larger molecules. And here, of course, the main issue is the validity of the continuum approximation. So, you need to average much more over time and so forth, unlike in the case of a molecular system. But still, a lot of these ideas can be applied. Now, in this class, I'm going to tell you about the simplest version of this kinetic theory. Okay. And this was developed in 1984. There are, of course, many more theories that are available, and even now, if you go in 2021, you will see some new papers have come out on kinetic theory of gases applied to granular systems. But this one will at least give you an idea of what are the main elements of this theory, and we'll solve a few problems because this theory is so simple. We can actually solve some problems using this theory. So let's suppose we have a volume we just consider a volume. There's a big system and we are considering a small volume in there. And let's suppose each of these particles has a velocity Ci. So each particle I has a velocity Ci. And let's say this volume is V and that there are n particles. Of course, this volume is large enough to get a good average. So you want an average in which there are several hundred particles, and you don't want to take an average which is of just a few particles. So then, but it has to be small compared to system size. Okay. So then we can define the mean velocity at a point, let's say at this point, which is at the center of the volume. We call that point as x. So then the mean velocity at point x is simply equal to the summation I going from 1 to n of C of I divided by n. Okay, so this is what is known as the mean velocity. It's just the number average of the velocity. You just add up all the velocities and divide by the total number. And we can call this by the angular brackets to say this is the average velocity. And then we can define, so this is the mean velocity. We can then define a fluctuation velocity of every particle, and I'll call that as V of I. This is just equal to Ci minus U. So for each particle, we can find out what is the fluctuation velocity. So by definition, if we take the average of this, then this is equal to average of Vi is just equal to average of Ci minus U, which is equal to average of Ci minus average of U, which is equal to average of Ci minus U. U is already an average, so if you average it again, it doesn't do anything. And this is equal to 0. So obviously the average of the fluctuation velocity is equal to 0. However, the mean square average is not equal to 0. So that means this will always be greater than or equal to 0. And we'll call this, let's call this as just equal to V squared. And this is just going to be greater than or equal to 0. So here V is nothing but the RMS velocity. I mean, in kinetic theory, you remember if you did any kinetic theory of gases, this is nothing but the root mean square RMS velocity. And we see this in kinetic theory, and just like we do in kinetic theory also, we can define using this fluctuation velocity, we can define a temperature, and here we'll call this the granular temperature. So we have the mean velocity, the fluctuation velocity, and then the granular temperature, which is based on the fluctuation velocity. And here we define this granular temperature as just 1/3 of T squared. And this has units of kinetic energy per unit mass. So this temperature is defined in this way. In kinetic theory, I just put, if you go and look at any book on kinetic theory, you will see that in kinetic theory, the temperature is defined as 1/3 mv squared. But then, there is a factor called kb, which is added here. So kb into T, where kb is the Boltzmann constant. So if you write it like this, you can see the difference. One is there's the kb is missing. In our granular temperature, we don't need this. And of course, we don't also put the mass in. We could, but we haven't put it in. So in this particular theory, drop the mass as well as kb. If you include kb, then it gives you the temperature in Kelvin. We will get our temperature in this energy per unit mass units. Okay. But in principle, both these temperatures, they essentially give the same thing. They give you something related to the kinetic energy of the molecules. So granular temperature, we can say, is just the kinetic energy of velocity fluctuations. And that is the same even in kinetic theory. The temperature is related to the kinetic energy of the velocity fluctuations. Now, one of the approximations that is made in half theory is, this is not necessary, but just makes things a lot easier. That approximation is of constant bulk density. So what he wrote down is that, if you look at the bulk density, this is just the mass of the particle divided by the volume occupied by the particle. I'm going to call it as V star. And the whole idea is that every particle, let's say, has got a sort of diameter which is d, and then there is, let's say, a spacing s between it. So then we can write this volume that the particle occupies is just pi by 6. And instead of just using d, I'll say, okay, it has that additional space s also, so d plus s cubed. So it actually occupies a volume which is like this. I should draw it a little better. So you should, this sphere will go around half like this. So this is s by 2, then over here also there will be s by 2. So that's why it's d plus s whole cubed. So this is a very simple way of putting in. And so the bulk density would be approximately given by some constant C1 into m. Then you'll have 6 divided by pi into d plus s cubed. Now, if s divided by d is much less than 1, that means if s is much smaller than the particle diameter, the spacing between the particles is much smaller than the particle diameter, then this is approximately equal to 6 C1m by pi d cube, which is a constant. So basically what you say is that the changes in density are very, very small. And this is true for all of these granular materials, that usually the change in density makes very little difference. But as we will see, this spacing S is very important. So though density we take to be constant, we won't take S to be constant, because as S reduces, then the effective viscosity of the system, increases a lot. So that's why this S will always be kept as one of the parameters rather than the bulk density. And so now with this as a background, let me write down the governing equations. For this half theory for rapid flow. And in here, the first equation is the continuity equation. And that is simply divergence of V is equal to 0. That is because, I'm going to keep making this mistake. V is the fluctuation velocity and U is the mean velocity. That's why it's divergence of U is equal to 0. Then you have the momentum balance equation. And this is just rho bulk into del U by del T plus U dot gradient of U is equal to minus gradient of P plus divergence of tau plus rho V into G. So if you look at this equation, this is exactly the same as what you would get for fluid flow. The difference will mainly come in the definition of P and tau. And then one additional equation that we'll always require is the energy balance equation. And in this one, what you will get is 3 by 2 rho B to del T by del T plus V dot, U dot gradient of T is just equal to is just equal to what? This is the thing that you have. So if you see this, here of course our temperature, as we have done before, is just 1/3 V squared. So we can even write down all of these things very easily in terms of the velocity. I mean, we can substitute for temperature as 1/3 V squared, and then we'll get an expression in terms of the temperature. So if you see this, the first point is that continuity and momentum balance equations are the same as for fluid flow. So that is one thing. Now if you look at the energy balance equation, most of the terms are the same as for fluid flow. And I look at the terms, this term comes in fluid flow, and if you remember it, this is nothing but the viscous dissipation. This is basically, if you think about in a liquid, when you shear the liquid, there is some amount of work done, and as a result of that work, the temperature of the fluid will increase. So this is the increase in temperature due to the shearing of the fluid. And similarly for a granular material, when you shear it with a mean velocity u, then the fluctuation kinetic energy increases or the granular temperature increases. So this is the term due to viscous dissipation. This is also there in fluids. Then you have, of course, divergence of Q is equal to 0. This is conduction. So, the kinetic energy of the fluctuations can transmit, but through collisions and so forth in space, and that is analogous to conduction. And this is also very much seen in fluids. And of course, on the left hand side is convection. U dot gradient of T term is the convection term. This is also seen in fluids. However, here this is the dissipation or loss of energy due to inelastic collisions. So this never comes in fluids. So this is only granular. Because there is no inelastic collision in fluids. So this is really the only extra term that comes in as far as the equations are concerned. But of course, as we will see, the form of P, tau, and IE and Q, these are all very, very different. Now, kinetic theory gives us all these, it gives everything, all the constitutive equations. Constitutive equations essentially tell us the material properties. They're based on the material behavior. So governing equations are balance equations. They will tell you, okay, mass is conserved, linear momentum is conserved, energy is conserved. So those are balance equations. Those are true for every material, but you need constitutive equations to tell you how a particular material behaves. And so these are, you can say, material properties. And so what are some of the constitutive equations? Let me write some down. So one is, for example, an equation of state. You know, for an ideal gas, an equation of state is PV is equal to nRT. So similarly, for a granular material, we can write as this: P is equal to alpha rho B D into T divided by S. Remember this S is the spacing. So you can think of S as something related to the volume. So you can see that PV is equal to something into T. So this is like nRT. So it's very much like an ideal gas. And over here, this alpha is just a constant. D is the particle diameter, rho B is the bulk density, T is the temperature. So this is one constitutive model. So this tells us that if you change the temperature, how will the pressure and change? And this is obtained through dimensional analysis, and what it says is pressure is directly proportional to the temperature. Then a very important second equation is the stress constitutive equation. For fluids, we are very familiar with the stress constitutive equation for a Newtonian fluid. And so here also we assume the same equation to hold, that tau is equal to 2 eta p, where d, as we have seen before, is nothing but half of gradient of v, gradient of u, sorry, plus gradient of u transpose. So this is exactly like that for a Newtonian fluid, a generalized Newtonian fluid, you can say. But for a granular material, the viscosity is just given by eta 0 rho b b squared square root of t by s, where again here eta 0 is some constant. So you can see, if you look at this is a dimensionless constant, alpha, eta 0 are all dimensionless constants, and if you look at the dimensions of rho b times d squared into root of t by s, you will see that this has units of viscosity. Then the third constitutive equation is for conduction. And here also we assume that it is just k times gradient of t, where k is the thermal conductivity, and so this is like Fourier's law. But of course, k is equal to k0 into rho b d squared root of t by s. Okay. Where again now k0 is a dimensionless constant. And then of course there's this dissipation loss. I'm calling it as IE because I is already the inertial number, so just not to get confused. And again here I0 is a constant. And E is the coefficient of restitution. So here we are. This essentially completes the full description of the theory. If I just sort of scroll backward, I will just sort of have written down so many things. So the whole idea was that, okay, particles are like molecules, so we'll use kinetic theory. We define a mean velocity u and a fluctuation velocity v. The average of the fluctuation velocity is 0, but the average of the velocity squared is not 0. We call that as the RMS velocity. And then the temperature is just the RMS velocity squared divided by 3. That's very much like the temperature defined in kinetic theory. Then we define this parameter S, which is the spacing between particles, and we take the spacing to be very small compared to the diameter. And so that's why the bulk density is a constant. And then we can write down the balance equations, which is exactly the same as for fluids, except for this one term, which is due to inelastic collisions. And then we write down the constitutive models. These are all obtained entirely by just dimensional considerations. This is the pressure, this is the viscosity, this is the thermal conductivity, and this is the dissipation loss. So now if you look at this, if you just count all the variables and all the equations, which maybe we'll do in the next class, you will see that we have a complete set of equations and we can actually solve some problems. And from the next class onwards, we'll start solving